Modern thermal power plants operate on a staggering physical scale, but the thermodynamic output of these massive facilities relies entirely on a microscale dependency: pulverized coal. To burn with optimal efficiency, raw coal must be ground down to the exact consistency of talcum powder. The singular mechanical choke point responsible for achieving this precise fineness is the BHEL XRP vertical bull mill. In heavy industry, these pulverizers operate as sealed block boxes. While the mill is actively crushing tons of coal, plant operators have zero internal visibility of the grinding process. Trusting a blind, unmonitored mechanical process at the micro level jeopardizes macro-scale thermal efficiency. Original equipment manufacturers dictate a rigid 12,000-hour replacement schedule for the mill's internal elements. Long before that calendar schedule is up, the physical geometry of the steel degrades continuously and invisibly inside the casing. Over these operational cycles, the heavy grinding parts lose their exact shape. As the internal geometry wears down, the finest of the pulverized coal drops proportionately. This drop in fineness starves the boiler of optimized, readily combustible fuel. The plant absorbs this inefficiency. It becomes a massive, silent operational expenditure bleed. You bypass the physical casing mathematically by implementing motor current signature analysis, or MCSA. Shifting from OEM calendar schedules to MCSA mapping establishes a data-driven baseline for identifying and managing this operational bleed. Grinding mills reduce particle size using three distinct mechanical principles. The first is crushing, which applies direct, heavy pressure to fracture the coal. The second is impact, relying on kinetic strikes to shatter the material. The third is attrition, the particle-on-particle grinding that creates the final dust. The rotational speed of the vertical mill dictates the optimal balance of these three forces. Inside, an internal sorting mechanism separates the adequately ground coal and rejects larger chunks back into the grinding zone. The ultimate metric for acceptable particle size is the 200 mesh screen. Plant performance guarantees dictate that exactly 70% of the coal must be fine enough to pass through this microscopic 200 mesh. A secondary metric requires 99% of the material to clear a slightly wider 50 mesh screen. This exponential increase in microparticle surface area provides macro-level flame stability inside the boiler. Achieving this specific surface area guarantees the effective utilization of carbon, preventing fuel from passing through unburned. Mastering these internal micromechanics is the foundation for the plant's overall thermodynamics. The primary wear elements executing this physics inside the machine are the grinding rolls and the bowl segments. Their durability is tested constantly against the Hardgrove Grindability Index, or HGI. The HGI measures the wild, unpredictable variations in raw coal hardness that the mill processes continuously. This graph plots mill output percentage against total moisture in raw coal. It shows exactly how moisture mathematically penalizes and reduces expected mill output capacity. This second chart shows the capacity correction curve for HGI. It dictates the mathematical compensation required when the mill encounters harder variations of coal. This technical schematic illustrates the physical failure mode. Continuous friction against hard coal slowly erodes the exact geometry, labeled here as dimension X of the grinding rolls. This localized geometric wear directly causes a severe drop in output fineness. To compensate for the loss of optimal geometry, the plant system automatically reacts by pushing higher hot air pressure through the mill. However, performance-guaranteed test logs establish a strict safety threshold. Differential pressure cannot exceed 300 millimeters of water column. This geometric degradation forces thermal plants to absorb severe efficiency losses months before the scheduled maintenance dates arrive. You do not need to physically open a machine to assess its geometric wear. Motor current signature analysis reads the machine's electrical shadow. MCSA correlates fluctuations in the motor's electrical draw directly to the mechanical resistance of the grinding elements. Specific physical changes in the internal geometric wear predictably alter this electrical resistance signature. You fuse this MCSA electrical data with the established differential pressure metrics. This dual data stream calculates and maps the exact two-dimensional geometric wear of the XRP parts, entirely without a physical shutdown. Real-time electrical telemetry replaces the calendar-based assumption with a measurable record of the mill's internal geometry. Once the machine's wear is mathematically visible, the financial reality of procuring spare parts changes immediately. Real-time wear mapping instantly exposes the true metallurgical quality of any installed spare part. Compare the sustained wear curves of premium engineered spares against cheap third-party materials. Cheap materials cause the geometric wear curve to accelerate prematurely. This triggers a steep drop in thermal efficiency, creating a hidden financial bleed. This accelerated physical wear completely consumes any upfront cost savings achieved by purchasing cheaper parts. Industrial supplier evaluation must prioritize a part's proven ability to maintain strict HGI and moisture capacity curves, not its initial purchase price. Advanced telemetry gives silent hardware a legible voice. This continuous data stream removes the original equipment manufacturer's advantage of controlling the maintenance timeline. Restorative engineering and data mapping allow operators to capture the industrial control point, making maintenance decisions based on hardware performance rather than service contract defaults.